Welcome to CS250, Data Structures using C++. This is a programming course that is standard to computer science curriculum. Let's talk a bit about what we will be doing this semester. This course is about data structures, but what are data structures? Well, to be literal, they are structures built to store and work with data, but maybe that's not enough information. Learning about data structures includes learning to build structures that store their data in different manners, such as storing data linearly without a meaningful order, otherwise just known as unsorted, data stored in a tree structure, which can make searching faster than with an unordered list, and storing data in a queue or a stack type structure, where you can only access the front of the queue or the top of the stack. As an example, let's store data in a list and in a tree. We'll store A, B, C, D, and F. How would we write an algorithm to find D in the list? We could start at the beginning and keep checking each element one by one until you eventually find it, and this would take 4 checks to ensure that D is found. But since this list is sorted, perhaps we could do it in a little more intelligent way. We know that D is closer to F than it is to A, so it's closer to the end than to the beginning. So perhaps with this check we could do a search from end to beginning instead of beginning to end. So if we go backwards, we just check F and then D, so we only have 2 checks. But if the list weren't sorted, there wouldn't be a good way to intelligently search the list. If we just stuck to beginning to end, it might be fast, like searching for B, or it might be slow, like if we were searching for A. Worst case scenario, we'd have to look through the entire list to find our item. If we wanted to keep the list sorted, then extra work would pop up when we insert a new item. If we insert something that belongs in the middle of the list, then we have to take time to shift elements around so we can place our new item in. This can also be costly in computing time. But while we add overhead during our insertion process, keeping the data sorted ensures that our search can be done intelligently and speedy. If we're going to use a binary search tree data structure, items can be inserted in any order, and the structure automatically stays sorted, as part of its insertion algorithm. So after we insert D, then we insert B, and it automatically goes to the left, because B comes before D. Then, if we insert F next, F is greater than D, or it comes after D, so it will go to the right of that node. Then if we insert C, well, C is less than D, so we go left, and then C is greater than B, so then we go right. And so this is the algorithm that you use to insert things into the binary search tree. Next, if we insert A is less than D, so we go to the left. A is also less than B, so we go to the left again, and we insert A to the left of B. Inserting this way takes up more time than simply throwing data on the end of an unordered linear array, but it's about trade-offs. As part of insert, things get put in an ordered place. With binary search trees, we have a series of nodes. New items with a smaller value go to the left, and new items with a larger value go to the right. Then if we want to find F, we start at the root node, which is D, and ask, is F less than D? No. Well, is F greater than D? Yes, so then we will traverse to the right. We move to the right and check this node. So now we found F. We only had to check D and F to get our result. The search algorithm is similar to how the insertion algorithm works, so they actually have the same average efficiency. So this is just a quick example of some of the things we will cover and be concerned with in this class. In order to gain a good foundation in data structures, in this class we will cover the following topics. First, we will learn about implementing data structures, like linked lists, queues, stacks, dictionaries, binary search trees, heaps, and balanced search trees. We will also think about design, including using exception handling and writing tests. And a data structure isn't very useful if it's very inefficient, so we will also spend time focusing on measuring algorithm efficiency, using Big O notation, and learning about searching and sorting algorithms. Additionally, it is important to have a solid foundation in core C++ concepts, so during the class we will spend time reviewing topics like pointers, memory management, object-oriented programming, templates, and more. If you're feeling weak on these topics, you should spend some time reviewing these. Sometimes this class can be challenging. A few tips for doing well is, if you can't figure out how to implement some functionality, try to sketch it out on paper. So for example, with an insertion algorithm, draw out on paper how you would insert 1 item, then 2 items, then 3 items. Also, getting acquainted with these topics requires practice, so make sure you have plenty of time to code. And make sure you have a solid grasp of core C++ topics. Make sure to review and practice if you have difficulty with some of them. Make sure to also ask questions if you're feeling stuck. Keep working at it. Try different things. No code will happen if you don't start writing code. So sometimes it just takes trying some small things and going from there. Also, data structures aren't a secret. There are a lot of resources online that you can reference if you still have questions after the lectures or the book. Check online. There are free ebooks, there are lessons on YouTube, there's source code on GitHub, and plenty of other reference pages online. Make sure you understand how each data structure works. You don't really need to memorize the code, but if you know how it works, you should be able to implement the code whenever you need it. That's all for the introduction. I hope that you enjoyed this course. Ask the instructor questions at any time if you need help with a topic, or keep in touch with other classmates so that you can study together.